All right, today we're going to talk a little bit about GMAW and FCAW, which stands for gas metal arc welding, otherwise known as MIG welding, and then flux core arc welding. Even though we're not going to do flux core arc welding in this class, it's still kind of important to kind of talk about because there's a lot of similarities between GMAW and FCAW. So we'll kind of mention a little bit of those differences as we go through, just so you have a little understanding that that welding process does exist. So when we talk about gas metal arc welding, or MIG welding is kind of the slang term that we use for short. MIG welding stands for metal inert gas. Basically, we're striking an arc between base metal and a solid wire. So unlike doing shielded metal arc welding, where we have a stick electrode, we now are going to have a wire that is coiled up, and it's going to be a continuous wire. It's, I don't know, it's 35 pounds, but you never run out. You don't have to like change rods or anything like that, so it's a little bit easier. With GMAW, we use a shielding gas that's going to come from a tank, so much like we do with oxy-fuel. Instead of having a flux on the outside, we're going to have a shielding gas that we're going to use that's going to help prevent it from getting any of the oxygen, nitrogen, hydrogen within that weld. Anything that's going to cause porosity, that's what our shielding gas is going to do. The one thing with MIG welding is it cannot be used outside because we are using a gas. Any kind of wind, even a small little gust of wind, will blow that gas away. You'll no longer have shielding gas, and you're going to get porosity. We may find with this process that if we forget to turn the gas on at first, or if we don't purge our lines out to make sure we get any air that's left in those lines out before we start welding, you may end up seeing porosity on your first couple of welds. Really easy to kind of see. We'll probably demonstrate that in class so that way you can kind of see that. Flux core arc welding is similar in respect to MIG welding, but the difference is we use a hollow core wire, as you can kind of see in this picture down here. There's a flux that is on the inside. So this flux is very similar to shielded metal arc welding, except instead of being on the outside, it's now on the inside of that wire. And so when that flux burns, it creates a little shielding gas. So runs fairly similar as far as, being able to weld outside, being able to weld in different, areas, because you have a heavier gas that's not going to get blown away. So you're not going to get porosity if you weld with flux core arc welding outside. So it's a different wire versus a solid wire that we use for MIG welding. This one's going to have the flux that's going to be on the inside. You can use, excuse me, you can use a shielding gas with flux core arc welding, and that's would create a process known as dual shield, where you have the shielding gas and the flux on the inside. And that's becoming more and more popular, especially in structural welding, kind of replacing a lot of the 7018 welding that's been done in the past. That's really the main difference. Otherwise, for the most part, they're kind of the same process where you have a continuous fed wire that's coming through. And you can kind of see that coil there and how much wire is kind of coming through. This is something that we don't often have to change unless we are using a lot of it. It's something that kind of stays there, which makes it nice, not changing rods out, not running out mid-weld, having to restart, prevents us from having to do that, or eliminates having to do that. They are continuous fed wire. Okay, the wire in our case is what we would consider our electrode. So that's what we're using to kind of arc against those things. So when we talk about DC electrode positive, DC electrode negative, we're thinking of the wire as the electrode. Our negative is still, our ground clamp. That process is not going to change at all. We just need to plug in where our wire is coming from into our positive. And there's a video that shows us how to actually connect the XMT welders with that thing. The flux core arc welding process is used only with ferrous metals and nickel-based alloys. Ferrous metals are things that contain iron. Okay, so as long as it contains iron, we can do that. That means we can't do it with like aluminum, but stainless steel, mild steel, we can do the flux core arc welding process with that. With GMAW, you can do aluminum welding, you can do stainless, you can do mild steel. You have to change out the wires. Sometimes you have to change some equipment out. We'll talk about some of the equipment later on in this presentation here. So self-shielded, the flux core arc welding, okay, basically we have a gas that forms once those things burn. the hollow inside where we have that flux is going to burn up. You're going to end up having a slag coating just like you do with shielded metal arc welding as you're going through and doing this. When we're doing MIG welding, we don't end up with that outer shell because it's only a gas. There's not any kind of materials in there, whether it be like a cellulose or a potassium, like we do within the shielded metal arc welding stuff. So flux core is kind of similar to both shielded metal arc welding and GMAW. And gas shielded flux core arc welding, or otherwise known as dual shield, we have that combination, as I mentioned, between both of those things. You can weld a little bit hotter, you can get a little bit more penetration. It kind of shields it a little bit better. It's a process that is pretty effective at getting high quality welds and then minimizing the cleanup that we have to do afterwards, which is why a lot of people are really going to a dual shield. We don't have to chip off as much slag and all that kind of stuff with that. They can use flux core arc welding with fully automated machines, so that you can have like robotic welders that are doing that, and they're running those things because we're not having to change out rods. You've got that continuous coil. We can use those things with that, and you can use GMAW with those as well. As I mentioned, we use the direct current electrode positive for GMAW and flux core arc welding. You can go into a negative if you're running some thinner metal, thinner stuff, but you're not going to get that penetration, especially on the thicker 1/4 inch stuff that we tend to weld on with these processes. They're what we consider a constant voltage machine. So this is different from the shielded metal arc welding where we've been focusing on adjusting our amps. In a MIG welding system, you're going to be working on adjusting your voltage. Your amps are going to be dependent on how much electrode stick out you have and the arc gap that you are doing. So you still have an effect on amperage, but the machine is going to control the voltage. So there's a little dial that we change to set it to MIG welding, and then instead of changing the amperage, we're going to be changing the voltage. And wire speed is the other thing that's going to change the amperage as well. So we set a wire speed, we set a voltage, and then the rest of it has to do with when we're actually welding, how far away we are keeping it. So we still need to keep gaps, we still need to keep certain distances, just like we do with the shielded metal arc welding. But instead of having things burn down and feed it down, you just need to keep it at a constant height, which makes it a little bit of an easier process to kind of go through. There are really two methods when we talk about MIG welding, and we're going to do both of these in this class. There's a thing called short circuiting, and then there's the process of transferring the metal across the arc. And under those, there's kind of 3 categories that we kind of see and demonstrate within there. We see globular transfer as one of the things that we are doing. We see spray transfer, and we see pulsed spray transfer. As 3 different processes. We'll go in a little bit more in depth in these things as we go through. Short circuiting uses low current, which is controlled with the wire speed. It is useful on really thin metal if we want to fill large root gaps, poorly fitted parts. It can be used in all positions. So we can do it in flat, we can do it horizontal, we can do it in vertical positions or overhead. There's very low heat input into the base metal, so you're not going to get a lot of penetration with a short circuiting system. We're going to use some of those other processes if we're really focused on getting that heat of penetration within that metal there. The way that this thing works is the electrode's going to come out of the gun, and it's actually going to, that wire is going to touch the metal. It's going to short that out. It's going to burn that little piece of metal up. It's going to deposit it into the metal. It's also going to melt that base metal as it's going through. When that does that, it actually cuts the arc out, and then the wire keeps coming down. It touches again. So it's arcing, no arc, arcing, no arc. It's very hard to see this because of the rate that this is happening at, but if we were to get a slow motion camera, you would actually see that it's arced and then there's no electricity. Then it's electricity, no electricity, and it's touching, arcing, touching, arcing. So that's what we call the short circuit system. It's called short circuit because we are cutting the circuit out and then kicking it back up again. But that's one of the reasons why it's a little bit colder, why we can use it on thin metal, because we're able to control that heat because we're not having an arc that's constantly burning that metal through. In a globular transfer, in globular spray and pulse, there's a little bit of kind of a gray area of where we're at. We have a range that's going to be a little bit higher than the short circuit. Typically, I say short circuit is around 18 volts and below. Globular transfer is kind of between like 18 and like 21. Kind of depends on where we're at. So there's a gray area in there, but it's just slightly above that short circuit. Instead of arcing when it touches, okay, what happens is it arcs a little bit before and it creates a big old blob, and that blob is essentially just thrown into that metal there, and it kind of slams into it, helps melt that base metal, and then deposits that the weld bead on there. If we're using an inert gas, it will drop straight into the weld pool. An inert gas is a gas that doesn't react with anything. We'll talk a little bit more about those as we go through. If we use CO2, you're going to get lots of splatter with a globular transfer. So you're going to get those things that we see in shielded metal arc welding. So the gases that you use is really kind of dependent. This is kind of an example of that globular transfer as it comes down. So the arc, it will actually create an arc before it touches, okay, and then those droplets essentially just melt and then they slam into the base metal there, causing it to burn. So it's not going to, you're going to be able to get a deeper penetration into your base metal because there's a constant heat within this system. Spray transfer is a little bit different. Our current and voltage settings are a little bit higher than globular transfer. We tend to say about 22 or 21 volts and above would be considered a spray transfer. With these ones, because you're increasing that voltage, you're increasing the heat of that arc, and so you're going to get finer droplets. You're not going to get a big old glob. You're going to get very fine droplets, and a lot of them repeated one after another. You're going to get really deep penetration. You're going to be able to direct this stuff a little bit easier than a globular transfer. You get a very stable and concentrated arc, unlike those other two that we've already talked about. These ones can be done in flat, horizontal. You can do vertical on these things, but really it's vertical down. Vertical up is a little bit tougher with a spray transfer because of the heat that we're creating as we're welding. That pool will just kind of melt out of there. So in this thing, you could see this picture here where we have the electrode is melting, and you can see a bunch of small droplets. So unlike short circuit where it's touching, this again is like globular where it doesn't touch, but it melts it a lot quicker. Instead of getting a big glob, you get the small droplets in there that are all slamming in, melting that base metal, getting that penetration. Pulse spray transfer is similar to a spray transfer. The difference is we have a control unit that's going to increase like highs and lows. When we start talking about the current, we have like a sine wave, and we can kind of change that where we get the high and then the lows of the electrical current there. What that does is it allows us to kind of control that heat a little bit better. We can do out of position welds because of that. You're still getting that heat, but then it's allowing it to cool down. So it's not like a short circuit where it's going to touch. It's like a spray where it's going to melt that, but then it's going to cool that stuff down because it's going to be in its lower areas. So we have special equipment that works with that. We're in this class going to do a spray transfer and a short circuit. So you're going to do both of them so you can experience that, both with some thin metal and then with some thicker 1/4 inch metal as we go through. So it's kind of similar to that. It just gets to the spray arc, just gets a little bit more control over the heat that you're inputting within that system there. These are kind of all of them side by side with each other. You can see the short circuit, you can see the amount of penetration, how wide that bead's going to be as we're kind of going through globular spray and then pulse transfer there. So it's a little bit less, but still getting us the heat that we need within those systems. Typically, a MIG welding station is going to have, these components in there. You're going to have something that can do a constant voltage. in DC power source. With the XMT welders that we have, those things are a multi-process unit. Some of the old, if you know what a Lincoln Tombstone welder is, those ones do not have the capability of adjusting voltage. We can't do MIG welding with it, so it would require a different machine. Some machines are MIG welders that are set up. We have like Miller 252s. Those things are only MIG welders. We cannot do any kind of shielded metal arc welding on them because all they're focusing on is controlling the voltage. So there's different types of machines for the different processes. Some are multi-process where you can do multiple things by changing some of the settings there, and that's what those XMTs that we have are. You're going to have some sort of feed mechanism for your electrode. You're going to have shielding gas cylinders. So in the shop, they are located kind of outside, just on the edge. And then we have a whole system that's fed in for all those boosts. Sometimes you can have a standalone unit and you'll have a gas cylinder that will be on that unit. So somehow we got to have a gas cylinder. We got to have some sort of regulator to regulate that. Or you might have a flow meter. So you may have one or the other, or you may have both. We'll show some examples of what those things are over here. You're going to have a MIG welding gun that's designed to kind of contain that wire there. You may have, that gun's also going to hold the shielding gas. You may have coolant hoses and fittings, so they may have like a water-cooled gun or an air-cooled gun. Most of the time, air-cooled guns, especially if you're welding in lower temperatures, lower voltages, an air-cooled gun is what we see. The coolant guns are when we start getting in the higher voltages. We're welding for long times. It's going to help cool that gun down a little bit from that heat. And then you're going to have an electrode wire, and those wires can vary in their diameter and style and what type they are. So we can change those things out as we need to. This is kind of an example of that system where you got all those separate components. Sometimes they're kind of combined into one, but you're going to have that power supply. You're going to have the control system for the wire feed to be able to feed that wire, gas that's coming in to feed that. You're going to have a gun. This is going to be an auto torch, or if we have a manual gun, basically they're going to look like this, where you've got a coil that's going to have your wire and your gas is flowing through, and a little trigger. So you pull the trigger and it starts that whole system. You let go of the trigger and it stops the system. Ground clamp is still going to be negative, still going to go onto your workpiece there. So they do come in, the wires come in large coils and drums that typically they're about 35 pounds. I'm not sure, but it's like, I don't know, like a mile of welding wire or something like that. Well, right here it says hundreds of thousands of feet. So it lasts for a long time, especially in the classes that we. Sometimes they're contained within the machine, sometimes they're contained without. So in this example, you can see that the wire wheel is separate. On your XMTs, it is a separate unit that we have to get, but sometimes it's all contained within the wire itself with the power supply. Like we can see right there. So this is like a separate unit system that we would basically plug in. So you need a power supply that this then plugs into. And that's what we're going to do in this class. Is there's a cable that comes down from here, and instead of electrode, that cable is going to come in and plug into the positive from this machine into the power supply that we have. This one's nice. This is a system that has two different wires, so you might have like a flux core wire, and then you might have just a regular MIG welding wire on either side. Or you can have different systems. You might have some stainless steel and some mild steel. Without having to change out everything, because you got to feed that wire all up and through that gun. There's drive wheels, there's motors that are on the inside. The video on how to set it up demonstrates those things and talks a little bit about that stuff, which you may have already watched. If not, you can watch it. It'll be posted on Canvas. And you can kind of see the inside and how those drive wheels work. These machines do have an inch or jog switch, so as we're trying to control the machine or feed wire through, you can actually like hit a little lever. Let me see if I can get to it here. The inch or jog switch is typically going to be, looks like it's right here. So you would hit a little lever down and it's going to feed that wire through, but not put an electrical current that's going to be live, that's going to arc. So if you're trying to adjust the machine or feed wire through, you can do that. They also have a gas purge valve on here, which allows us to hit that that lever. So when we first start up, you want to hit that gas purge valve to kind of purge out your hose line in your gun. Make sure that you have the gas that we're using to help kind of support that stuff there. So purge switch and that stuff will be on there. But we'll demonstrate that stuff. If we don't demonstrate that in the video, we'll demonstrate it in class for sure. The regulators that we use are similar to the oxy-fuel ones, but these ones are designed a little bit more specifically for the gas that we're using. Sometimes these things are like multiple gases, so you can see like CO2 and argon. We do use different types of gases with arc welding or with MIG welding, and so the regulators have to be adjusted for that. Gases have different weights, and so reading pressures and things like that is dependent on the type of gas that we are actually using. We also have flow meters, so you might see some flow meters on these things. Flow meters and the regulators are similar. The difference with this flow meter is it's going to have a tube with a little ball that is going to float, and that's going to tell you how much CFH, or cubic feet per hour, that we are running. It is only going to be running, that ball is only going to be floating when gas is flowing. So we can use that purge valve to actually float that ball up and get that gas to actually flow. When we don't have that running, if the machine's on but we're not actually running that machine and gas isn't flowing, this ball is going to fall to the bottom. So you're not going to take a reading. You have to hit that purge valve and then adjust your regulator to get the correct flow that you need from there. Regulators like this, they're going to tell you the pressure all the time. So in the tank systems and the manifold system that we have, this is plugged into the tank, and we set our pressure up for our manifold, and that's going to hold steady whether it's flowing or not. And then typically at each of the stations, we're going to have a flow meter that we're going to adjust for the proper gas flow. We typically want anywhere between like 20 and 25 CFH running through. It's kind of dependent, but that's a good range to kind of start from. Too little, you're going to get porosity. Too much, it's going to blow your gas out, and then you're going to end up with porosity as well. So you want to kind of find that medium in between there. The shielding gases that we used can be inert. That means they are not going to react. Things like argon, helium, those things are inert gases. They're not going to react with different stuff. Stuff like oxygen is going to react to fires, and so that's what we would consider a non-inert gas. They're not going to react to other things. They're not going to do that. The nice thing with using inert gases is that we don't need to bleed the lines out like we do with oxy-fuel. With the oxy-fuel, because they're not an inert gas, they could cause a fire to become bigger, and so we want to make sure that we're not, we're draining those lines out and they're contained within the tanks. So we can shut off the tank so we don't have a leak and drain our whole tank, but we don't have to bleed the lines out at all. That gas can just sit in those lines until the next time we come in. So the reactive gases are going to react with other ones. So oxygen, CO2 is a reactive gas. Obviously, acetylene is a reactive gas because they're going to do that. But carbon dioxide and oxygen, we can use those things for MIG welding as well. We do use hydrogen and nitrogen, sometimes in very small amounts for specialized applications. If we're doing like a stainless steel weld, we'll use a little bit of hydrogen, maybe a little bit of nitrogen. Or if we're trying to get a little bit more heat, we can kind of combine those things. And very often we see mixtures of gases that are going to use. It's not just a solid gas that we're going to use for these processes. So probably the most popular one is what we call a 75-25, 75% argon, 25% CO2. And it just helps with, getting in that penetration as we are welding within these things. Typically, if we're doing any non-ferrous metals, so things that would be like aluminum, we're going to use argon, we're going to use helium. Okay, those are going to be the two. We might use just argon with a little bit of helium, or just a straight argon with that. Helium is going to allow us when we have like a high heat input needed. Helium is really good because it allows that heat to transfer very, very quickly. Helium is a very light gas that allows heat to transfer quickly. Argon is a very heavy gas, and it allows that heat to kind of travel a little bit slower. Argon's also a little bit cheaper than helium. Helium is expensive. It's important to note that the helium that we're using in these systems are not the helium that you use in balloons. These are highly purified helium that we use for welding. So you don't want to take a helium tank for blowing up balloons and try to use it for welding. You're going to end up getting a lot of porosity within those systems. This is an example of kind of different gas mixtures and the penetration and stuff that we get within these systems. We have an argon gas that we use that is going to create potentially a little bit of undercut in there. We can use an argon oxygen or an argon CO2 mixture within those two, and those things are going to be a little bit better. You're going to get decent penetration, typically a little bit less undercut within those systems. If we're using a straight helium, you'll notice the bead's going to get a little bit wider, but your penetration is going to be a little bit less within that system. Argon helium combination, you're going to get a little bit more penetration, still kind of a wider bead. And then if you use a straight carbon dioxide, you're going to get a lot of penetration within there. You're going to get a lot of splatter on the top of those things. So very often we see the argon CO2 mixture because that is good penetration, good width of your bead. And like I said, a 75-25 is very common for that stuff. So we use a 75-25 mixture. You can do a 90-10 mixture. You can do any kind of combination that you want. But the most common one we see is a 75-25. So if you order gas, you're saying 75-25, that's going to be the mixture that we want. Carbon dioxide, it is a reactive gas, but if there's a fire in the shop, it's going to put out the fire, not make it bigger. So we, still consider it kind of an inert gas in terms of safety for bleeding out the lines. Moisture-free carbon dioxide must be used. Otherwise, carbon dioxide will grab moisture within the air, and we don't want water to be mixed in with our welds. Proper length, if we're using just a straight carbon dioxide, is really important. It is the least expensive shielding gas, so that's why sometimes you see that. But it does cause a lot of issues with splatter and other things as we're going through. To overcome that mixture of those things to flow, we're going to use that gas mixture. Like I said, an argon CO2 is very, very common for what we see. Sometimes you'll see oxygen, and even though oxygen is something that causes porosity, it will allow the heat of that to, kind of burn a little bit deeper. And what happens is the argon actually sits lower because it's heavier, and the oxygen's up a little bit higher, so it's not actually getting into your weld. They kind of separate out because of the weight of those things. You do have to worry a little bit about porosity if you have the wrong pressure set up within this stuff. For flux core arc welding, we use self-shielding stuff. Those things are going to be the most common gas that we're going to use with those things is going to be a carbon dioxide if you're using a shielding gas in addition to that. But there's other ones that we can use, other combinations that we can use, depending on the process that we have. Talking about the equipment now, the MIG welding gun, the primary function of the gun is to direct the electrode and to also direct your gases within that system there. They do have, inside of these MIG guns, there's a thing called a liner that is built into the gun that helps guide that wire. The gas is then going to go on the outside of those things. Air-cooled guns, they just use the natural ambient air to kind of cool this gun because it will heat up as we go through. But there are water-cooled guns that has water actually pumping through the system, all up and through the tip to help keep things cool as we get higher pressures there with these things. They do have other styles of guns. The one that we saw before is typical, but when we talk about the wire-cooled guns and like push-pull guns that we use with aluminum, they're going to be a little bit different. We also have spool guns that we can use on top of things. So if we want to have a spool gun, your wire is actually kept in the little top piece right here. If you look at the image at the top there, that's a spool gun. I'm personally not a big fan of those things. I don't think they work as well as other guns. Down in the bottom corner there, you can see a water-cooled gun with the blue and red lines there. So that's your water that comes in with those. You have to have a separate pumping system, or it might be built in to use a water-cooled gun there. But it just pumps that stuff up in there and helps kind of cool that, cycles it through like a radiator does on a car. A push-pull gun is going to be used with aluminum as well. You have to have the spools that are pushing from the reels, and then you actually have gears that are up inside this gun pulling that wire. With aluminum wire is kind of weak, and so if you try to push it all the way through that gun, it's actually going to bend, and so we use a push-pull gun if we're doing MIG welding with aluminum wire, and that's what you can kind of see in the bottom left corner there, is that the push-pull gun there. We do have, welding guns that are doing automatic stuff. Those handles are typically going to be straight. It's going to have a mounted system that's going to have motors and servos that are going to direct it on a track, or if it's a robotic arm, it's going to move it around. And basically, it's just you set up the system to run at a certain speed, and it can run down the line. You set up your metal there, and it can weld those things. Takes out that human input, that human error that we can have, and so a lot of places are going to these things, especially manufacturing, where you're repeating the same weld over and over again. They'll use those things. So slightly different gun there. On the inside, we have things called contact tubes, nozzles, and liners that are on the inside. Some of these things need to be replaced. The contact tubes, this is what you see in this picture. Those things will get kind of, welded. They might burn up a little bit. If you're using them properly, they may not, but if you've got high heat, they may burn up a little bit easier. The contact tubes have to be matched with the size of the wire. So a typical wire that we use with MIG welding is an 035 wire, but they have 045, 030, 050. They're all different sizes. The contact tubes have to change, or contact tips, as they're also known, can we do that. Typically, they're made of copper or copper alloys to help direct that electrical current. So these are the things that are helping take that electrical current and direct it into the wire. If you use the wrong size tube, the weld's not going to come out very good, or you're going to have an unstable arc as you're welding. The nozzle is on the end of the gun there, and that nozzle helps kind of contain that gas within that system. These things do fill up with splatter occasionally, so there's a dip that you can dip these things in to prevent splatter from contacting it. But we also have MIG pliers that we can use to kind of clean these things out. Nozzles you can the liners you can kind of see in the inside of the gun that goes in there. This directs the wire within that system there, and then the gas flows on the outside. So that runs in that whole length of that gun. These do get clogged up after some time, so sometimes we do have to replace those things from time to time. The wire that we have within these systems is going to be a continuous solid wire, and they're wound up into spools like we can see here. That's going to help. That's actually carrying the electrical current. So the current goes through the wire as we're going through. So, the size of the wire, like you could see here, an 030 wire. We can do a stainless steel wire. Just have to change out the gases if we're doing stainless steel wire, but any MIG welder can weld with stainless steel. And that is kind of a fairly popular system, unless you're doing anything that is going to be in a food grade. Food grade is going to require TIG welding to do that. But if it's something that you're just welding, like it's just a stainless steel table that you want to not rust, stainless steel MIG welding is going to be appropriate for that system. Filter lenses and gas shielded arc welding, because we have a clearer shielding gas within that system, we want to make sure that we have a darker shade lens. Shade 10 typically works for us in the amperages or the voltages that we're running. But if you have something that you're welding a little bit higher in voltage, you'd want a little darker shade lens. So you might go with 11 or 12. That's going to help reduce the eye fatigue and possible damage that you might have within that system. Most helmets for arc welding use a clear cover lens and a filter lens. So you have a clear cover that's going to be on the front, and then your lens is actually going to be behind that, because they can burn up. You can get splatter on there to help kind of fix those things out.